So let me get to the topic of the day. So this is timing filtering techniques for RF front ends. This is a somewhat broad and fairly quickly evolving topic. So I'm not going to pretend to cover all aspects of this thing. Many of you are probably aware of much of these things already. So I'm going to focus on one particular aspect of this, which has been the center of my group's focus for the last few years. Okay. So, but before I get there, let me acknowledge that much, if not all of this work here is done by excellent graduate students, three of whom have already got PhDs on this work, and a fourth one who's just about to get maybe in a few months or so. Mansoor Rashid, Samid Hamid, Neha Sinha, and Dr. Shibu. The research has been primarily sponsored by National Science Foundation. Some of the students have also been supported by the Broadcom Fellowship, Foundation Fellowship, and the Qualcomm Innovation Fellowship Foundation as well. Okay, so now let me give you a brief outline. So I will very briefly talk about the problem in RF front ends. Then I will introduce the particular time varying approach that I'm going to discuss today, which is filtering by aliasing. It's somewhat of an interesting name and needs some explanation, so I'm going to go into the details of that thing. The main idea is to use sampling aliases to help sharp filtering. That is somewhat unconventional, so I'll spend some time talking about that thing. I will show how we can use this idea to design fairly sharp filters. Filtering by aliasing filters is what we call them, but they are general time varying circuits. Hopefully the examples will give you an idea as to how to use or how to build these kind of filters. Then I will talk about one or two examples, more realistic examples where we apply this sharp filtering technique, time varying filtering technique to relevant practical problems. My focus primarily would be on agile RF front ends and time permitting, maybe a little bit on spectrum scanners. A lot of interesting applications are coming up where you would want to send spectrum very quickly. So I'll very briefly talk about it. Okay, so what is the RF front end problem? For those of you working in circuits, this is probably obvious and apparent, but still for those of you who are new, the main issue is that in the RF front end, you want to extract a very weak desired signal shown by this green curve, green part of this power spectrum, PSD sketch here. And this is a very weak signal generally. It could be anywhere depending on the frequency reuse plan and whatever. But you want to extract this thing from among a large number of interferers, many of which are significantly stronger than the weak desired signal, and whose frequency location can also vary in time. Okay. Now, you ask the COM theory people, their solution is, it's not a problem. Just throw in a very, very good ADC right at the antenna. And they have even given it a name. They call it a software-defined radio. For those of us who are building circuits, we know that, well, that's possible as of today only in measurement equipment. Is that kind of an ADC which can handle up to a few gigahertz of bandwidth and hundreds of dB of dynamic range is simply not practical in the form factor of a small smartphone or so today. The other approach, which is what has become fairly acceptable, is to have a tunable analog front end. The analog front end what it does is it basically effectively does filtering. It removes out much of the blockers, the interferers. Now, by removing the blocker, what you are doing is that you are making the job of the ADC easier. So the ADC can operate with a lower bandwidth, lower resolution, and you can extract just the desired signal, and then you get what you want. Now, obviously, there are issues of sharpness versus tunability and linearity trade-offs in this front end. This front end should be able to, typically the bandpass filter, you want to be able to tune it to whatever frequency desired signal you want to reside in. You may want to change the filter shape depending on whether you are looking for a narrower bandwidth or a wider bandwidth and things like that. Perhaps the biggest problem is that while you are filtering, you don't want to incur substantial nonlinearity, because if you incur substantial nonlinearity, then these interferers, they can fold back on top of the desired signal. And since the interferers are very strong, they could overwhelm the signal even before you do any further digitization and so on. So this is the RF front-end problem. So if you really take a closer look, the fundamental challenge here is that of aliasing. So let me explain. Like I said, you basically want a filter to extract the desired signal, and there are blockers outside the filter bandwidth. If the blockers interferers are not suppressed sufficiently, when you sample this filtered signal, they will fold back onto the signal, and then it is difficult to separate them. So all the way back to our undergraduate days, we have been told that you want sharp filtering prior to sampling to avoid the aliases. That's where the Nyquist condition, Nyquist rate came from, and all of those conditions. And that's really what all of us have been doing as RF front-end designers or circuit designers. Build really good filters so that we can suppress all the signals that would otherwise alias, and then we can simply digitize really clean. Now, filtering is a difficult thing. There are very good filters. For example, passive filters like SAW, BAW, and MEMS, they are very linear. Problem is they're usually bulky and not very programmable. So in the initial days, this was fine, but later on, when you had to deal with multiple bands of frequencies of operation and so on and so forth, programmability became a big problem. The solution, typically accepted solution, is to have several banks of these kind of filters, each one acting or taking care of different frequency band. That usually leads to a lot of area, a lot of cost, bill of materials cost, and so on. The other approach is to build active filters. Active filters are programmable because you can change things on the chip. They can be very programmable, but the problem is they are power hungry. And even if you are willing to live with the power consumption, they are generally not linear enough. If they're not linear, like I said earlier, the blockers will fold back onto the desired signal, and that can cause quite a bit of a problem, distortion. So this is the primary challenge. So we went back and asked ourselves what needs to be. Now, other people have also looked at this thing. Active RF front-end priority is a very mature field. For the most part, people have tried linear time invariant approaches to this thing. More recently, last 10 years or so, researchers have achieved great progress in doing time varying circuitry for this thing. I'm showing you a few of the approaches here. The bottom right quadrant is somewhat of a different approach. I'm kind of grouping these approaches into very coarse categories. Some of the research reported out there may not fit nicely in one of these categories, maybe an overlap of two of these categories. But bottom line, there is this charge domain filter approach where they get very sharp, linear, precise filtering by essentially realizing a discrete time filter. Okay, this has been pioneered by a lot of researchers. Bogdan Starzyewski, one of them. There are several others as well. Peter Kingett's group has done quite a bit of stuff in this area and so on. Another approach is mixer first receivers, where they have where they present a frequency selective baseband impedance that gets up-converted and shows up at the RF frequencies. That way they can do even sharp first order or second order, or these days even third order kind of filters at baseband. And depending on the LO frequency, they move up to the appropriate LO RF frequency, and they can get very good filtering there as well. And the other approach is so-called N-path circuits. N-path circuits are fairly old, but in the last decade or so, they have seen a resurgence. These are very interesting circuits, time varying circuits, and they can get very good linearity and sharp filtering as well. So each of these approaches has its own advantages and disadvantages. For example, the top two approaches, the charge domain filtering and the mixer first receivers, they usually have an upfront LNTA. So all the linearity burden falls on the LNTA. The NPath circuits, they have their own issues. The out-of-band filtering is somewhat limited, although there are new interesting approaches on that thing. Professor Bramnauta's group and Klumpering's group in Europe, they have done some really interesting work on this thing where they have demonstrated outstanding linearities in the order of like 45 dBm IIP3, if I remember correctly. So there's a lot of interesting work that's going on in this thing. The approach on the bottom right is somewhat of a signal processing approach called compressive sampling. The idea here is that at the RF front end, while there are a lot of blockers, given the wide spectrum, you could still treat it as a sparse spectrum where there is a desired signal somewhere and perhaps a few blockers somewhere whose positions could be changing and whose positions, frequency locations you don't know of ahead of time. So what they do is they kind of randomize the signal using a pseudorandom sequence, and then they filter it, and then they sample it at a much lower rate. The idea being in the sampled content, there is content from all of these blocker signals, a tiny part of it in the sampled content, and then they do fairly sophisticated L1 based recovery algorithms, signal process recovery algorithms to get the signal back. Now, this is very promising, and there's been some work, particularly from Yonina group in Israel and Peter Kingett's group at Columbia. Definitely in the area of spectrum scanning, this is very promising. Effectiveness in full-fledged receivers has not yet been demonstrated. Now, again, like I said, this is a fairly quickly evolving and a fairly broad field, so I'm not going to go into the details of all of these things. What I will do is I will describe our approach, which is somewhat different from this thing, but shares some similarities. Primary commonality between these approaches and our approach is that these are all time varying. So if you look at all the approaches on this slide, something or the other is varying in time. For example, you have switches that are switched in and out. And so on. That's what happens in the charge domain filtering. In the NPath circuits are also based on switching to a different capacitor and different clock and so on, right? Same thing with mix-up receivers and so on. What we said is that let's take this concept of varying the circuit to its next logical step. So we said, how about if you could change or the value of entire components in time? If you make it truly time varying, what kind of advantages can we get and so on? Okay, we have been primarily conditioned to make things linear time invariant. That's what we've been primarily doing. All of our undergrad as primarily circuits undergrad education has primarily focused on designing linear time invariant circuits, right? So making them time varying opened up a new set of possibilities, analysis issues came up and so on and so forth. So my primary here is to give you a feel of what kind of advantages can this kind of an approach present, what kind of challenges are there, and what kind of progress we have made so far, and hopefully what is possible in the future if we go down this route. Okay. So with that preamble, let me get to this central idea of ours, which we call as filtering by aliasing. It's basically a time varying circuit. So let me describe it. Simply put, we want to address this notion that we have to remove the aliases before sampling head on. So our approach is that we are going to precondition the signal such that the sampling aliases, rather than corrupting our signal, the sampling aliases will combine destructively. That way, they are not going to bother our signal that much. That's the idea. So what kind of signal conditioning can we do? Our approach is to do a time varying signal condition. So for example, in the block diagram on the left here, there is preconditioning block. Now, this is not the only way of doing this. This is one way of doing this, a simple way, easy to understand. So what do we do? So in this case, we take our desired signal x of t, which has a desired signal. Maybe for illustration's sake, let us say it's a DC signal, close to DC at the 0. And there are interferers, let us say at fs and minus fs and so on. So in this case, if there were no blockers, let us say it is sufficient to sample the signal at fs. Okay. But because there are blockers, if I sample at fs, then these blockers are going to fall right on top of my signal, and that's going to cause corruption. So normally you would filter out the aliases before doing the sampling. Here, I'm not going to filter out the aliases sharply before sampling, but instead, I'm going to precondition. And what's the preconditioning? I'm going to take my input signal and I'm going to multiply it with a periodic signal d of t. This d of t has the same period as my sampling period, ts. ts is just 1 over fs. And then I'll follow it up with a very simple filter, like a first order RC or a simple integrator or something like that. And as I'll show shortly, by choosing this periodic waveform d of t appropriately and cleverly, you can make blockers or the sampling aliases combine destructively upon sampling. So the result would be as if the blockers are very strongly suppressed and you are left primarily with the desired signal. Now, a tiny bit of residual blockers may remain, and I will discuss that thing towards the end of the talk. So first of all, the first big hurdle in dealing with a system like this thing is it's time variant. So our general analysis methods, which are based on Laplace transforms and Fourier transforms, don't really work very well here. But fortunately, because it is time varying, it turns out it's actually fairly easy to understand what's going on. Now, since I'm eventually going to sample the signal at Ts, let us consider the samples. I know it is very early in the morning for equations, but please bear with me, it's just a one-line equation. So we know that the output, the sequence of the samples y of n, it's basically taking y of t and sampling it. And y of t itself is nothing but a convolution of h of tau, the impulse response, and the product of x and d. So on the top right, I have the simple expression. It's fairly easy to see. I can see the convolution in the product of d and x with h, and I'm sampling it at t is equal to nts, where n is an integer. Now, d of t is periodic. That means that d of nts minus tau is going to be equal to, the typo here should be d of minus tau, right? It doesn't depend on ts because it is periodic. So accordingly, it turns out that as far as the samples y of n are concerned, if you are looking only at the samples y of n, this is equivalent to a system where the input x of t goes through an effective impulse response g of tau, and then it is being sampled. And what is this g of tau? This g of tau is nothing but the product of the original impulse response h of tau and d of minus tau. Remember, d is a periodic signal, so d of minus tau is the same as d of ts minus tau, right? So at first glance, it looks like I have made things more complicated, but not really. Now, this h of tau could be a very simple filter, like a first order RC or a simple integrator, which is chosen to give you low power consumption and very good linearity. Generally speaking, in the past, when you have to make a very sharp filter or a complicated, sophisticated filter, that's when linearity and power consumption, all those things become really big problems. But if you are do a very simple RC filter, linearity is not a problem at all, right? So h of t is very simple. The idea is that if you want a really sharp programmable filter, you can choose your d of t such that you can tailor the impulse response g of tau. In other words, you can precisely engineer the effective impulse response g of tau. And how do you do that? By realizing a precise d of t. Now, fortunately, digital to analog converter techniques have advanced quite a bit, and these days you can realize fairly precise D2A, D2T, precise analog waveforms with these sophisticated digital to analog converter techniques very well. So we're going to use that d of t. We're going to put intelligence in d of t. We're going to control d of t very precisely, such that the effective response is very sharp and very linear. The main filter h of tau is still a simple one, like an integrator or a simple RC. So overall linearity will be very, very good. So that's the theme. And I'm going to show you examples that it can actually be done and actually get very good linearity. Now, this is a time point of view of what is going on. So let me also give you a frequency domain point of view, because I've been claiming so far that I'm really using the aliases to help me give me better sharp filtering, right? So let me take you through the frequency domain operation as well. So this is somewhat in, so I have a little bit of an animation here. Hopefully that helps. Okay, so let's take a look at this. Let's start with a simple example where I have a DC, a low or a frequency signal. And let us say there are two blockers, Fs and minus Fs. Okay. You can extend principles for a general purpose local oscillator, multiple blockers, and so on. But just to keep things simple, I'm ignoring the local oscillator. I'm considering a low pass filter and simple blockers at Fs and minus Fs. And now d of t is a periodic signal. So its Fourier transform will basically be a bunch of spikes at Fs and 2Fs and 3Fs and so on, right? So I am considering a simple case where there is something at Fs and minus Fs, just for illustration's sake. Okay. Now multiplication in time domain is convolution in the frequency domain. So when I convolve this Fourier transform of the signal plus the blocker and the d of t, what I get is I get copies of the signal and the blocker at Fs and 2Fs and so on, shifted copies, translated copies, right? So you can see the signal shows up at DC and Fs and minus Fs according to the coefficients of the d of f at DC, Fs, and minus Fs. Similarly, you have copies of the blocker at Fs and the blocker at minus Fs and so on. They're all shown. Now, if I were to simply sample this signal, all these copies fall on top of each other. The blockers will fall on top of the signal, and the signal is going to be completely corrupted. But suppose I filter it with a very, very simple filter. For example, let us say a low pass filter or an integrator, as I'm showing you on the bottom right. That's a simple integrator's response. It's high at low frequencies and low at high frequencies. So filtering is multiplication in the frequency domain. So what happens is that the various copies of the blocker at various frequencies, they are all differently attenuated by a different amount. This is frequency selective. And now if I sample, again, these residual copies will fall on top of each other. But if I were to choose my d of t properly, I can make it such that when I sample them, the copies of the blockers that fall on top of each other can cancel out. If I did not do any filtering, then that won't work. Then if I simply sample, all the blocker copies will fall on top of each other constructively, and you will have a bad problem, aliasing problem. But because they are frequency selectively attenuated, now if I choose d of f properly, then what happens is that after sampling, the signal can be made to be constructively, signals copies can be made to constructively interfere, and the blockers copies can be made to destructively interfere. And that way, what I'll have is my desired signal and a tiny residual blocker. Of course, this will not work for any d of t, but what I'm saying is that I can choose my d of t such that this happens, right? In the time domain explanation also, I said the same thing. I can choose my d of t to make my effective filter very sharp. So this is the frequency domain point of view. As you can see, it is really aliases of the blockers, the aliases, the sampling aliases that are kind of interfering destructively to cancel out the blockers. That's why we call it filtering by aliasing. Rather than suppress the aliases, I'm going to exploit their presence in a clever way and cancel them out. Okay. So in summary, basically what I'm saying is that it is as if I have effective filter whose impulse response is g of tau, which is a product of the simple h of tau and d of minus tau. Like I said before, h of tau is a simple filter that is chosen primarily for its linearity and low power consumption, something as simple as an RC or a first order integrator. And the D of t is what I really use. It gives me extra degrees of freedom to finely tune the effective impulse response. Okay. And since data converter, D2A converter techniques are very advanced, I'll show you shortly that D of t can be controlled very precisely. In our own chips, we have shown that you can easily do up to 10-bit, 11-bit just with DC calibration. Okay, so let me give you a couple of examples how I can take this somewhat abstract concept and show you can actually realize a simple, very sharp filter. So I'm going to give you two examples. One is an active RC circuit, other one is a passive circuit, to really illustrate the potential of this kind of a technique. So let me start out with the active RC technique, which is easier to understand. So on the top left, you see a block diagram of our approach. The Rin of t with that weird circular arrow around it, that is our symbol for a periodically time varying resistor. The circular arrow suggests that the R value is going to change periodically. I know there are other symbols out there with similar thing, but we kind of stole that symbol because it conveys our intent fairly. The circuitry within this dashed box, that is our simple filter. It's basically a windowed integrator. That means it will integrate for a finite time of a finite width of duration Ts. And at the end of this integration period, I sample it. In other words, this is also what is known as an integrate and dump. So integrate, sample, and then throw the charge away and dump. Okay. So as your Rin of t is varied, so I'm going to give an intuitive explanation of what is happening here. As you change the Rin in time, the current flowing into this integrator is changing. So in other words, my Rin is going to realize the D of t. In fact, you can show that the effective D of t is 1 over Rs plus Rt, right? Because that is the effective resistance seen by the input signal, so the current changes in inversely proportional to that. Now the integrate and dump, like I said, as a simple filter, which is 1 over impulse response is 1 over C, integrates from 0 to Ts. Okay. Intuitively, what's happening is that this realizes an analog FIR filter. The duration of the FIR is Ts, 0 to Ts. And during the duration, the individual signal values at different times are weighed by a different amount controlled by Rin of t. So you can show that this is effectively an analog FIR filter whose impulse response is basically 1 over C times Rs plus R of minus tau between 0 and Ts. Beyond that, it is 0. This is analog FIR. Standard discrete time FIR design methods can be used. You can discretize this G of tau, and then you can choose what your R should be to get a very nice linear phase filter. Okay. The sharpness of this filter really is only limited, well, how precisely you can control this filter is really only limited by how well you control R, right? And that's the basic idea. I'll give you an example. So the figure on the bottom left shows you an example resistor variation over one period of time. This is a periodic variation. I'm going to repeat this variation every period. So this is varying from 0 to Ts according to this blue curve. You can see that the variation is quite dramatic. It varies all the way from, I think, about 15 ohms or 13 ohms all the way to maybe around 8 kilo ohms. So it's about 2 to 3 orders of magnitude of variation. Okay. But 2 to 3 orders of magnitude of variation is what I'm doing. And the figure on the right is the effective filtering at the sampled output. Okay. Now we have to be a little careful here, because what I'm saying is, this is the filtering seen as far as the samples are concerned. So let us say in this example case, I'm sampling at Fs is equal to 5 megahertz. So the actual Nyquist bandwidth is 2.5 megahertz, 0 to 2.5, right? So when the input is a sinusoid between 0 and 2.5, this is like a simple sample, a simple filter, and the filter response is blue curve. But when the input is, let us say, at, I don't know, 51 megahertz, right, or some high enough number. So what it means is that that input sinusoid is going to see this effective filter given by this blue curve. And after the filtering, it is going to get sampled, and the residue is going to fall in band. So there is filtering and sampling happening together implicitly in the same block. Okay. So the blue curve is the effective filter. So for example, if I look at 25.1 megahertz input, that means that 25.1 megahertz input is going to see a 60 dB attenuation, but then it's going to the 60 dB attenuated signal is going to fall in band at about 0.1 megahertz. Okay. To compare with a traditional first order integrator or first order filter, I'm also plotting the first order response. That's the dash red curve. That's a simple first order filter. Why am I showing that? If I did not do any time variation here, if it were an LTI circuit, that's what I'm going to get, a first order filter. But because I'm doing this time variation, what I have is an incredibly sharp filter. This is about equivalent to a sixth or a seventh order filter. So this is what really got us hooked on this approach. By taking a single component, one single component, the resistor, and making it cleverly periodically time varying, I'm able to get these incredibly sharp filters. And that was very, very promising to us. Let me talk briefly about how we're going to change this resistor. So obviously, changing the resistor continuously over time will be challenging, but you can always change it in discrete steps. You can switch it, right? If you do that, you're going to get images in the frequency response. But if you have a high enough switching rate, then the images can be easily pushed below the filter floor. So in our chips that we have built so far, as I'll show shortly, we can change the R of T at about a gigasample per second or so. In modern technologies, switching a resistor at a gigasample per second is fairly simple. It doesn't even consume much power because modern technologies switching speeds are really, really good, right? So this blue curve, the resistor variation, the top left curve, instead of following the blue curve, I will follow like a staircase version of the same thing, switching at some frequency FCK. Okay. And effective impulse response will be this bottom left red curve. So it's like a staircase approximation of the blue curve, but I still get an FIR filter essentially. So that was the active RC example. Now let me give you an even more ambitious passive RC example. This is a trivial circuit, the first order RC. This is the first circuit all of us have studied in our undergrads. We know that a first order RC will give us simple 20 dB per decade low pass filter. Now what I'm going to do is I'm going to change the R variation periodically at some period Ts, and I'm going to sample at the same rate Ts. Let me explain what is going on here. So at any given point of time, what's happening is that the current flowing into the capacitor, that is the current through the resistor, is simply X of t minus Y of t divided by the R, right? So that's what I'm showing you in block diagram here. Y of t is fed back, X of t minus Y of t. It is getting multiplied by 1 over R of t. So that means that's the current going to the capacitor. Okay. Now for out of band signals, the output Y of t is pretty much close to 0. So at least in the out of band signals, this can be approximated as the figure in the bottom right. So it's as if the feedback is not there. So this is an approximation, but effectively is easy to explain. That's why I chose this thing. But it is as if you have a signal X of t and you're conditioning it with 1 over R of t. And then you're going to a simple integrator. Now in this case, the integrator is not a finite integrate and dump. This is integrating forever, right? This is what I have. So you can do a little bit of math here. I have the equations for your benefit. I'll post the lecture slides, talk slides later on. You can look at it. The bottom line, what I want to convey is that it is as if I have a very precise discrete time filter whose coefficients are controlled. Coefficients are this alpha 0, alpha 1, beta 0, beta 1, and all of those things. And those coefficients are controlled by the sampling period, not sampling period, the rate at which you are changing the resistance value, TCK, the capacitance value, and the resistance value at that time. Okay. So by choosing this resistance value what I can do is I can control the coefficients of this filter very precisely. Now, unlike in the active RC case, this is not simply an FIR. This is actually an IIR. There are also some IIR poles here. But you can do standard discrete time filter design techniques. Go to MATLAB, get a design filter. We actually did some optimization as well, but you can achieve by choosing RFT pretty precisely, you can achieve really fine, very sharp, very precisely controlled filters. Let me show you an example. Here is our simple RC, time varying R. The figure on the bottom left is showing you an example resistor variation. Here I am showing you two periods. So the x-axis is normalized to the sampling period TS. So I'm showing you over two sampling periods to clearly show it is a periodic. Again, the variation is about between 2 to 3 orders of magnitude. And the figure on the right is the effective filter response. The red is what you get for a simple second first order filter. That means if there is no time varying, if it's an LTI circuit, you're going to get simple 20 dB per decade. But with this, I got a 7th or 8th order Butterworth filter. Now just pause to consider what I'm saying here. I took a simple RC filter, the poor RC filter that everybody has studied since their undergraduate years. All I did is I changed the value R fairly precisely at a fairly high speed. And then I sampled it. As far as the samples are concerned, this is like a 7th or 8th order filter. Now, from an implementation point of view, that R of T is like a resistor DAC. That means you have a bunch of resistors and a bunch of switches. The switches are not used as active blocks. They are only turned on or off to get a precise value of R. This circuit, by definition, is going to be incredibly linear because you're not using the transistors in their linear the mode of operation where the nonlinearity is a concern for you. Furthermore, as you go to finer and finer technology nodes, this switching the resistor is going to become easier and easier because of scaling. Transistors become smaller, they can switch faster, and so on and so forth. Okay, so I believe that this approach could be very, very attractive in a lot of different settings. So mine is a small group. I have only a few graduate students. So we chose to apply this technique to 1 or 2 example applications. And we are hoping that researchers all over the world will like what we are liking among this thing, take this thing and hopefully expand this into other settings. Just imagine what is potentially possible if you had a lot more components varying in time, or if your components are varying in a more sophisticated ways, what can be potentially achievable, right? Anyway, let me illustrate an application for a more realistic setting. So let me focus on the agile RF front ends. I'll just touch upon the spectrum scanners towards them. Now for an RF front end, what do we need? You need bandpass filters with programmable center frequency and programmable bandwidth. But that's not enough. You want to match to the antenna. You want antenna impedance matching constraints. You want to suppress the blockers, or you want to tolerate them. That means you want really sharp filtering. You want good linearity, and you want low noise figure. So the question is, the simple technique that I presented till now, it seems too good to be true. The question is, can it really hold up when you apply it to a more realistic system in presence of all of these extra conditions? So let me show you step by step how this can be done. Okay, I won't go too much into the detail, but just give you the basic idea. First of all, how to make it a bandpass filter. The circuitry I showed you before, for example, the active RC was a simple low-pass filter, right? Now, here we borrow ideas from the mixer first approaches, right? Well, to get a bandpass filter, all I do is throw in a passive mixer in there. If the passive mixer is at LO frequency or not, then the LO mixing effectively converts the sharp low-pass filtering FA, the sharp FA low-pass filter, to a sharp FA bandpass filter. Now, our filters are much, much sharper than conventional filters, first order, second order. So you're going to get a really, really sharp bandpass. Now, this was what we showed in ISSC 2016, and I think a VLSI paper at the same time as well. Next, let's come to the impedance match. Now we already know that getting impedance match in mixer first and npath is not an easy task. It's more complicated than, for example, getting impedance match in a LTI system. Here I have a situation where I am intentionally changing the resistance, that too by 2 or 3 orders of magnitude. So is it possible to get input match there? Let's consider this simple case. So if you, from the source side, you are basically seeing a varying resistance R of t. So in other words, what you're going to see at the source and the R of t boundary, you're going to see a periodically time varying reflection coefficient in gamma of t. Basically R of t minus Rs divided by R of t plus Rs. What does it even mean to have a periodically time varying reflection coefficient? Now consider I have an input which is a sinusoid at the LO frequency. So the reflected wave would be gamma of t times the sinusoid. Now we know that the reflection coefficient is periodically time varying. So if I get Fourier transform, I'm going to get a bunch of spikes at DC, Fs, 2Fs, and so on. Remember, the Fs is the sampling rate these are required for a single channel, right? If it's a 10 megahertz channel, Fs is as small as 20 megasample per second, which is much, much smaller than the FO, the LO frequency. Now, frequency domain is basically my input is a spike at the LO frequency. That's what I'm considering here. And multiplication time domain is convolution frequency domain. So the reflected signal will basically have a spike at F0 at the LO frequency. And I have another one at F0 minus Fs, F0 plus Fs, F0 minus 2Fs, F0 plus 2Fs, and so on and so forth. So really, in band, the reflection coefficient is effectively the value of the gamma F at DC. Okay, in other words, it is nothing but the mean value of the periodic reflection coefficient. So what I'm saying is that I can do input impedance matching as long as I focus on the mean value of the periodically time varying reflection coefficient. So now what do I have? So it means that I can still design my filter, periodically time varying filter, to get me a very sharp filter. But now I have to make sure that my S11, which is basically the mean value of my time varying reflection coefficient, I want to make sure that that is less than some alpha. Alpha could be my target, minus 10 dB or something is typical. That's what it is. So this is again a filter design problem, but it's an optimization problem. So I want to choose the R of t such that the constraint optimization problem. I want to choose the R of t such that my S11 remains less than target. Okay, so I have done this optimization, and here is an example. The blue curves correspond to the R of t variation when I did not have a constraint. The red curve is when I have this S11 constraint. Clearly, as you can see in the bottom left figure, the R of t variation is smaller now, so that I can meet the S11 constraint possibly. But the circuit still works. Of course, the effective filtering I get is not as sharp now. The stopband attenuation is not as good. It's only 40 dB now. But in principle, I can do it. Now, clearly, I don't want a 40 dB stopband attenuation because remember, my residual blockers will get aliased and I cannot filter them further. So I do want to get back to a very, very high stopband attenuation. So how do I get the stopband attenuation? Now, if you recall, we are realizing an analog, at least with the active RC, with this particular implementation, we are realizing an analog FIR. The best way to realize a much higher stopband attenuation in analog FIR is to simply make the FIR longer. So here on the XF, figure on the left is showing you two G of T's. The red one is a shorter one, the blue one is a longer one. It has twice the period. And the figure on the right is showing the effective filtering from that analog FIRs. You can see the blue one is 60 dB higher attenuation, stopband attenuation than the red one. So that's what I want to do. But I have a problem because my filtering by aliasing approach constrains me to sample the signal at the same period as the periodic variation. So if my T of t is periodic with 0.2 microsecond, then I'm forced to sample at 0.2 microsecond. That means I can get a higher stopband attenuation, but I'm sacrificing bandwidth. I don't want to sacrifice bandwidth. If I have a 20 megahertz band, I want to go to 20 megahertz. So let's get it again. What I have is I want to have a trade-off between the stopband attenuation and the bandwidth. Now, but that is known trade-off. It's the same known trade-off we have in ADCs. I can either get a wide bandwidth or I can get a higher SNR. So what do we do in ADCs? We do time interleaving. So we can do the same thing here. Imagine I have two of these filters, right? I'm showing you two filters here, each one with its own R of t. But the R of t is now periodic with 2 Ts. That means it can implement this longer period, longer FIR, the blue curves. So each of the filters has a much higher stopband attenuation, but they are lower bandwidth and they are also sampled at a lower rate. So what I do is I take the bottom channel and I simply stagger the sampling point. So that means I'm going to shift my R of t by Ts, and I'm going to shift the sampling point also by Ts. This way, if I interleave the output samples from both of these, I basically get back my original sampling rate, and I have my very high stopband attenuation. Okay. This is more math here. I don't want to go through the detail here. It's just an expression for the effective filter response. It turns out the effective filter response also makes it easier to get the S11 matching. Think about it like this. So I have two R of T's in parallel, and they are not the same. They are the same. They have the same periodic variation, but they are staggered versions of each other. So when one of the R of T's is high, the other one is low. So the parallel combination, the resistance variation is not as drastic or as dramatic as the individual case. So as a result, my S11 constraint also becomes easier. Okay. The figure on the right shows you what kind of filter attenuations I can get, at least theoretically. Now remember, remember that the R of T, in practice, it has to be quantized to some number of bits when you're practically realizing it. So the figure on the right is showing you what kind of filter responses I can get as a function of the DAC that is going to use that's going to be used to realize the R of T. The black curve tells me the effect attenuation I'm going to get, stopband attenuation. It's an ideal R of T, no DAC, assuming the DAC is infinite resolution. That's like close to 120 dB stopband attenuation. Now the blue, the green, and the red corresponds to DACs with 16-bit, 13-bit, and 10-bit, right? The 10-bit itself is about 80 dB attenuation. And this is just a resistor DAC, so we can do calibration, DC calibration, to get that target resolution we want. Okay, so for example, if you have a 10-bit DAC, you can get 70 dB or better stopband attenuation. Now, by the way, please note that you can trade off stopband attenuation for filter sharpness. In some situations where you want more stopband attenuation, but you don't care so much about the filter sharpness, you can trade off that thing. That comes from standard digital filter design techniques, nothing new or specific to this particular circuit technique. So here is an example realization of the resistor. So in our case, we built a 30-bit resistor, simple binary scale resistor. You can see R values. It's a poly resistance and the switch resistance, the switch gate. And we chose the poly resistance, the switch resistance to poly resistance ratio to be about 1:4. You can make it higher and lower. If you make the switch smaller, then it will have a larger resistance. So that means the power consumption in switching the resistors is going to become lower. That's good. But the switch is a transistor, so it can have some nonlinearity. So nonlinearity may not be as good. If you make the switch larger, so its resistance contribution will be smaller. That means the linearity of that thing will be much better, but you'd spend a little more power. We also played some circuit tricks here to take care of the effect of the capacitances and so on. When you're switching these things at a fairly high speed, the capacitors can limit how fast the DAC you can actually realize effectively. So you have to be a little careful, but again, with technology, This is only a trade-off that is in our favor. With technology, the R of CDS corner is only going to move higher and higher to help us. So let me skip this slide of more details of this thing. Bottom line, let me get to how we implement the simple integrators here. We did not do anything fancy. Simple, straightforward baseband integrator is an inverter. It's self-biased. This is a technique that we shamelessly borrowed from all the Mixer First and Empath folks from .com and Ramnauta's group and so on. Same old thing. So it's an inverter, a self-biased inverter. There are other techniques. We have not done anything different over there. Now, in our approach, we have to sample. The integration has to go for a 0 to TS, and then I have to sample that signal. So to facilitate that thing, the feedback or the integrating caps, we ping pong structures. They were implemented as MIM caps and ping pong structures just to make these things easier. So that while one capacitor is being used for integration, the other capacitor is being sampled, and then they change their roles. Here is an overall block diagram for this thing. So you can see two channels, or two time interleaving channels, R of T and R of T minus TS. In each channel, basically the LO is implemented like a 4-phase clocking or 25% duty cycles. Again, this is standard technique in Mixer First and Empath receivers. It easily gives us I plus, I minus, Q plus, and Q minus. That's basically what we do. So that's the two time interleaved 4-path filtering by aliasing blocks. This is the standard 4-path mixer clock generation. Nothing really different from ours and the traditional receiver approaches. This is the RDAC sampling waveform generation. Now this is basically digital. The R of T that you want, you store it as a sequence of 10-bit values in an on-chip memory. We use a register-based digital memory, but you put it in SRAM. To change the filter shape, you simply bring in a new R of T sequence. Okay, and that's it. So this is a very digital-friendly kind of an approach. Here is an implemented IC. This is fairly big, but that's only because we have a lot of programmability in the capacitor banks. These are test chip, prototype chip, where students' PhDs depend on, so we didn't want to take any chances. But you can see that the actual op amps and the LO switches and the resistor DACs that implement the resistor, they are not big, they are fairly small. The digital memory is also pretty small. And these 65 nanometer CMOS. You go to a more advanced technology, this is going to shrink greatly. I'm going to very quickly go through some example measurement results. This is just published in paper, so I don't want to take up too much of your time in that thing. Here I'm showing you measured filter programmability. The figure on the left shows you different filters, right? So 3 filters, black, brown, and the blue, and the red is a filter without time interleaving. So as you can see, with time interleaving, you can get a much higher stop band attenuation and so on. So what I'm trying to show is that by changing RFT, you can get a different filter. And that is very attractive in many, many applications, particularly in the receiver application. The figure on the right shows you programmability in terms of bandwidth. So to get higher bandwidths, all I do is I simply change my sampling rate, FS. To get 2.5 megahertz bandwidth, I do 5 megasample per second. To get 20 megahertz bandwidth, I do 40 megasample per second. The RFT kind of remains the same. The number of taps in the effective filter goes down a little bit, but the filter shape doesn't change that much. It is primarily determined by the length of the FIR rather than the actual coefficient. Here is LO programmability. Because the filter shape is kind of independent of the LO, we just kept the LO and you see different responses all overlaid on top of each other. In this case, we were able to show about 70 dB of attenuation. Here are measured receiver nonlinearity, linearity. The figure on the left shows you both IIP3 and blocker 1 dB compression point measurement. X-axis is the frequency offset. The dashed red line, that is the band edge basically. So you can see that the linearity is very good, right? The figure on the right is the IIP3 for different LO frequencies. This is about 21 dBm. Now this is an older paper of ours. This is, I think, maybe around 3 years or so older. Most recently, we will present something in next year's ISSCC actually, another version of this thing where we've been able to get up to, I believe, 38 dBm IIP3, if I remember correctly. Okay. So here is wideband S11 and the blocker noise figure. The S11 is pretty good, less than minus 10 dB for almost a gigahertz of LO frequency range. That is because we did a constrained design of the RFT. The blocker noise figure measurement is shown on the right. The noise figure is definitely higher than traditional filter implementations, and that is not surprising because I'm weighting the R of t all the time, and sometimes my R of t can become a pretty large value. So accordingly, I have a lot more noise. This is definitely a disadvantage of this approach, and I'll talk about briefly a little while later. The shooting up of the noise figure, that is primarily because of, well, the higher noise figure for higher clock blocker powers, that is primarily because of a lot more noise in the clock. And again, this is no different than traditional mixer first and blocker NPAT implementations. So here is a comparison table. There's too much detail to go through in a talk, but let me focus your attention on the red box. Again, like I said, this is about 3 to 4 years older, but you can see that our stopband rejection are very, very sharp. We're able to get 70 dB attenuation and the transition bandwidth only 4 times the bandwidth. Now, please note that this bandwidth is programmable. So even when I have a 2.5 megahertz bandwidth, I will still get a 70 dB, a transition bandwidth of 4 times that, right? So many of it's not like when I have a 40 megahertz bandwidth, I have a 4 times 40, which is 160 megahertz transition bandwidth. It's not like that. Even when the bandwidth is very small, I have a really, really good, very sharp transition bandwidth. So let me also show you that the outer band IIP3 and the blocker 1 dB compression point are really, really good. For example, our outer band IIP3 is 21 dBm at a blocker which is only 1.2 times the bandwidth, right? This compares much, much better than whatever is the prior art at that time. Again, this is 3 years older. Our most recent one, which we present at ISSC 21 next year, is about 35 or 38 dBm. Blocker 1 dB compression point also is similarly very good. Now let me briefly talk about subsequent evolution of this thing, right? I didn't want to spend too much time going into the details of this thing. So like I said, noise figure is higher. Why? Because I have my R of t changing, and sometimes the R of t can become very large. On average, I'm getting good S11 match, and I'm getting very sharp filtering. But the fact that the R of t is sometimes very large means I have a large noise figure, right? Now, RF front ends don't like that thing. So we also did other work on this thing. So I did not talk about this thing in detail here, but basically what we did is that we showed that you can actually do noise cancellation also in the time varying receivers of this kind. This noise cancellation is a little more involved than the standard noise cancellation that Broadcom and Bram Nota's group and others have pioneered and over the years. It is similar in vein. The primary difference is that now the cancellation path shown in red, that is also time varying. So we showed that we were able to get up to 3.2 dB noise figure. It's still a dB higher than the very best in state-of-the-art noise figure, but we do this thing without sacrificing the sharp filtering and so on. Now, another issue is channel aggregation. If you look at my R of t, I am presenting a time varying resistance all the time. Because I'm presenting a time varying resistance, having many such receivers in parallel can be problematic. Why? Because one channel might interfere with the other. Because each of them is varying in time, that could be a problem. So we set out to do channel aggregation. So basically we did some modifications that allows us to do channel aggregation. I'm not going to describe this thing here, but please, we'll present more details of this thing in ISSC 21, where we showed that we can get these very sharp filterings with channel aggregation. So let me briefly talk about another application, because I don't want you guys to think that this is only applicable at front end. We also want to show other applications where very sharp filtering is useful. I'm going to spend just a couple of minutes on this thing, but the slides are more detailed, which I'll make available to you. Now, in spectrum scanners, the structural similarity is there between with RF front end, but there's a little bit of a difference. With spectrum scanners, you want programmability with center frequency and the bandwidth, but you want excellent linearity, much more so than in the RF front end itself, because you are scanning over a much wider bandwidth. You probably have a lot more signals that are stronger and so on and so forth. And excellent harmonic rejection is needed because you're not looking at a small band, you're looking at a band that could be several gigahertz wide. And perhaps more than anything else, you want very low power consumption. You can always use a good receiver as a spectrum scanner by changing the LO. But imagine if you have interesting applications in security or privacy or defense applications, anti-jamming applications, and things like that. You want very agile, very low power spectrum scanners. So that's what, and linear spectrum scanners. So that's what we tried to get. Okay. So for that, we used our passive implementation. That means no amplifier, simply an RC, right? So I'm not going to go into the details here. If you vary or you can get a very, very sharp filter, the ones that I'm showing you on the right with about 60 dB or better stop band attenuation. The primary thing I'm going to focus on is the harmonic rejection. Now, if I simply multiply by an LO, a passive mixer, then what happens is that, if I simply multiply by an LO, then I will have image filters at the harmonics of the LO. So for example, at 3FC, 5FC, and so on. That may be okay in some RF front end, but not all. But it is definitely a bad thing in spectrum scanners because you could have a blocker somewhere at the 3FC or the 5FC, and that will corrupt your spectrum scanning. For a cognitive radio application, that's like disastrous. So for harmonic rejection, what we really want to do is we want to basically affect sinusoidal mixing. And we know this thing. Harmonic mixers essentially try to do the same thing. They have multiple LOs, different LOs of frequency, but multiple phases, and then we weigh them and add them. It's a standard harmonic mixer. In FA, it turns out I can do that thing very, very easily by simply realizing that multiplication by a cosine, a sinusoid, is the same as multiplying by a square wave and multiplying by the envelope of the square wave. And all I'm going to do is I'm going to combine the envelope of my square wave. I'm going to include it in my d of t, that is giving me my filter shape. So when I combine that, basically, I can get harmonic rejection literally for free. Right? So this is example harmonic rejection simulation plots showing fantastic implementation. Measurements show that, I don't think I have a plot over here. Here. Measurements show that the harmonic rejection is at least 30 dB for the third harmonic and about 40 dB for the fifth harmonic. More importantly, a structure like this thing is extremely linear and extremely easy to implement. Why? Because it is simply a bunch of resistors and a capacitor. There's nothing else in it. And the DAC is simply poly resistors and switches. So you can see that the resistors are much bigger than the transition gate switches. So the signal, only a small fraction of the signal appears across the switches. So accordingly, you get fantastic linearity for an implementation of this kind. Without getting into the details, let me show the result here. Our linearity is about 35 dBm IIP3, which is far, far better than anything. And this was about 5 years old work. Okay. What I liked as being a professor at a university, what I liked is this is arguably the least risky or the simplest of our projects. Why? There is really nothing in there. All I have is a bunch of resistors and capacitors and switches. The least risk. Imagine graduate students were still under training, implementing circuits, complicated RF contents, and so on. This by far was the least risky thing, because we get the system design right, it's almost a sure thing that it's going to work. Furthermore, the power consumption is also very, very low because there is really no amplifiers or anything here. Just to give you an idea, at that time, the hour power consumption was less than 8 milliwatt, which is like, I don't know, significantly lower than all the prior art. Now, of course, the sensitivity is not the best. It is lower than some of the works, but still comparable, good enough. Okay. The reason I'm bringing up the spectrum scanner is that I want to point out that interesting new applications could be enabled by this kind of an approach. All you had a simple RC, change the R very in a periodic time varying manner, and you have a spectrum scanner which is pretty good for just 8 milliwatts of power consumption. That allows you to do all kinds of interesting things. Perhaps you can put it in a cognitive radio scenario, or an application, a defense application, where you are looking for blockers, people trying to blow up IEDs, or even in simple spectrum reuse. Perhaps you can use this thing by having many such sensors all over the place for enforcement and policing efforts and so on. So in summary, what I've tried to show is that you can use sampling aliases to our benefit. It gives us sharp, integrated programmable filtering, and promises excellent linearity and low power consumption. So I showed that this demonstrated this agile RF front ends and spectrum scanners. And we got best in class in filter sharpness and linearity and power. Over the years, we have slowly started with simple filters, and now we are also being able to show channel aggregation in exercises. But from an academic point of view, I'm really encouraged by the fact that there's a lot of potential for this kind of an approach. I believe this kind of time varying can be extended to other circuit topologies and other applications. I can think of a few on the top of my head. For example, many medical front ends require sharp filter. Well, this could be a very cheap way of doing this. IoT devices, RF front ends and IoT devices usually have a power consumption issue, but they still want as sharp filtering and so on. You could use it over there. I think if you could do this kind of fantastic filter sharpness and linearity by varying single time varying component like a resistor, I am encouraged by the possibility of what we could do if we are willing to change multiple components in more sophisticated ways. There is a problem, a challenge, that is we really need good analysis techniques. We have done a little bit on this thing as well. I'm not discussing it here. Other people have also tried to do something similar. For example, Professor Shantipawan's group at ID Madras and so on. But still, on the analysis front, we are very far off from where LTI analysis techniques are. But I think if we can make some progress, I believe this could be extended to a very large set of applications. And here is a list of selected publications, but that's all I have. Thank you for listening patiently. If you have any questions, please.
Hey, Professor Pamarti, thank you so much for the excellent talk. At this point, let's go to the Q&A. So if you have a question to ask, please unmute yourself and ask away. Just while we wait for folks to do that, I do have a question. How sensitive is the performance of this technique when you have errors in getting the resistance versus time?
Yeah, so that's an excellent question, Alvin. So while I did not go into detail here, so what we did include is a DC calibration of the resistor DAC. All our filters are designed assuming a well-calibrated 10-bit resistor DAC. So we build about 12 to 13-bit actual implementation, and then we calibrate it one time at DC to get the 10-bit. So that is the sensitivity to the resistor variation, which is not that bad. Even with 10-bit, you can get very sharp filtering. So I think I had a curve, particularly with the time interleaved version. Even with 10-bit, you can get a very good filter attenuation.
Got
Having
it.
said that, let me mention one other thing. So I think I went a little too far back. So this green curve, that is a 10-bit DAC, right? I'm quantizing my coefficients to the resistance values to 10-bit. So if the resistance is not calibrated to, if it has errors below the 10-bit level, you will still get the green curve. Having said that, a bigger issue is the capacitors and other parasitics. Think about it like this. I want to realize a time varying resistor. That's like a resistor DAC, and I'm changing the resistances fairly quickly. For example, I'm switching it, let us say, at a gigasample per second. The R variation is not very fast. You can see the blue and the black curves and the red curves, they're not very quick, but there is at least maybe around 100 megahertz kind of content in there. So which means that I'm essentially trying to realize about 120 megahertz bandwidth DAC. If you think about it that way, then you can see that parasitics can limit you. Invariably, in all the implementations we have done so far, we found that the parasitics are the ones that limit you. And they seem to be limiting us to somewhere around 70 dB stop band attenuation. Okay. Now, is that a fundamental problem going forward? Maybe, maybe not. Now, our chips are older technologies, 65, one is 28 that I have not shown here. But if you go to finer technology nodes, I think that's going to improve. But can that be a fundamental limitation? Possibly. So if you had other architectures where perhaps you distribute the burden of the filtering onto multiple time varying stages, perhaps it could be better and so on.
Now, along this the line of my question, did you try to just intentionally create an offset, create an error in the resistance value, and see how quickly the performance degrades, or to basically check the sensitivity? I'm just kind of, my question is more related to, are you threading the needle with this technique basically, or it's still fairly insensitive to no errors?
Yeah, so it is fairly insensitive to the resistor errors. So like I said, this green curve is a 10-bit quantized version, which means that any error less than 10-bit value, we don't care. So when we do this quantization, for example, we try different versions. Sometimes we put in random noise, random errors in the various resistance values. As long as the RMS value is below the 10-bit level, then we are okay. Now, let us say that you do this calibration once, and with temperature, things change.
Yeah.
Right? Now, if the R changes with temperature, then clearly the coefficients can change. But that is not that bad a deal. If the RS is also going to change, arguably, then the whole thing will scale accordingly, and it is not a big deal. So that way also it is robust. Right? But definitely you need something at the 10-bit level. What we also found is that more than the stop band attenuation, the transition band shape is the one that is potentially sensitive to this. Try to get a 13 filter, then clearly the sensitivity will be more. So that's why we are saying if you do a time interleaving approach, then 10-bit sensitivity is just as good.
Thank you. Yeah, just a comment to add. I mean, 10 bits makes the resistor DAC potentially quite large, even though you may have stronger switches and all that. I mean, resistors are one of those things that are not really scaling from node to node into the advanced CMOS nodes, and it'll get prohibitively expensive. But yeah, it's okay. Yeah, it's just it's very interesting work. Yeah, and I'm assuming in all your switches, since you're very, very meticulously integrating charge and so forth, all the standard tricks like offset, cancellation for clock feed through, for charge injection, all that's probably stuff you have to pay attention to get this level of performance, right?
I mean, we do the obvious symmetry-based techniques, Like for example, if I have a transmission gate, then I try to make sure that those things are balanced and things like that. We did not have to do anything special.
Oh, wow. Okay.
One thing that we did do is that if the parasitics also vary in time, that complicates the effective filter shape. You can design for it, but the design becomes complicated. So what we have tried to do so far, and I'm not saying this is the only way, what we have tried to do so far is to come up with register DAC structures which try to minimize the parasitic capacitors time variation. So we try to make sure that the parasitics that are varying in time are minimal. We don't mind if a particular capacitance is fixed. That kind of things that we had to do. Definitely, this is not trivial by any account. But what we have found is that if you, like I said, if you were to do let's say 100 megahertz register DAC, whatever tricks, whatever things you would do, the same kind of things will apply here. Maybe not even like the offsets probably won't matter as much. So things like, let us say there is a particular parasitic, like if a particular parasitic is charged up to some value in one phase of the clock, when one particular register is on, and later on when I switch it out, we do simple things like discharging it. Otherwise you will have some weird code dependent time varying nonlinearities and stuff like that. So we do simple things like that, which are usually good practices even in simple register DAC design.
Cool. Okay. Thank you. Questions out there? Anyone want to ask some questions? Please just unmute yourself. You should be able to unmute yourself and ask Professor Pamarti the question. Any questions out there? So I do have another question I want to ask. The frequency range of interest, right? I mean, you're limiting this to basically 1 gigahertz or less, right? And so, I mean, are you targeting? I mean, would this be a technique that's more applicable? And given the technology node, the applicability of this being in a slightly older node, the applicability of the ideas towards like IoT kind of applications would be good. But what applications do you see, for the frequency range of interest, these approaches to be most directly applicable to?
So the frequency range, it is not necessarily constrained to 0 to 1 gigahertz. So let me explain, qualify it. The LO frequency can be higher. The filter, so because think about it like a mixer first structure. You have a baseband filter and that's kind of upconverted to the LO frequency, right? So a similar thing is happening here. I have a baseband FA filter, which is very sharp and linear, and I'm kind of upconverting that to the LO frequency. So the LO frequency can be higher. In principle, that does not limit us. Okay. The filter itself, how often I change the resistance value, that can place some limits on how wide a bandwidth I can get. So for example, so far we have looked at bandwidths up to around 20 to 40 megahertz, I believe, right? And we have been running the registers at 1 gigasample per second. If I want to, let's say, get a 120 megahertz bandwidth, if I'm changing the resistance only still at 1 gigasample per second, it is not enough switching within the cycle. Got it. Right? So that can limit the amount of sharpness I can get. But many of the applications we found so far are not of that kind. Now, but let's say if you go to a millimeter wave kind of situation, then the bandwidths over there are much wider, right? So I don't think it will be applicable there, at least as of today. Perhaps there is some other way of doing so. But the LO frequency itself can be pushed higher independently. Having said that, if I have these resistors and switches all showing up front, there will be some capacitance from those switches and so on. So they will have some impact on the S11, right? That's like a more LTI kind of a calculation, but it can present more and more capacitance as I go to higher and higher LO frequencies. But that is not that different from any of the NPAT or the mixed plus kind of approaches either, right? So that is where it stands. So I believe it should be possible to apply this thing to situations where the LO frequencies are higher. You may have to do some modifications. But if you want higher bandwidths without changing the clock frequency or the switching clock frequency, that could be trickier.
Okay, thank you. We did have a question. Professor Pamarti, I wouldn't want to put you on the spot, but question was asked if you can make the slides available
Yeah, sure.
after the talk. Thank you.
Sure.
So we'll just post it on our website if it's okay.
Yeah, sure.
Yeah, thank you so much.
No problem.
Any other questions?
Hi, I have a question. This is Sushil from Intel. So I was just wondering, particularly in the time interleaved case, it looks like you want to time interleave twice in order to improve your stop band attenuation, but at the same time keep the same sampling rate for the signal, essentially. So, but does it looks like the shape of the G tau doesn't the bandwidth of filtering doesn't really depend on the length of G tau, right? It's more depends on probably the coefficients or the shape of G tau. So basically, my confusion is the length of G tau doesn't seem to be determining the filter bandwidth. Rather, it determines the sampling rate. So how do we, if you want to design for a certain filter bandwidth, how do we choose G tau?
Yeah, so the way our system is set up, like for example, if I look at, let me go back to this one. So the way this is, maybe even this, the way it is set up is, if I'm interested in a certain bandwidth, then I pick my FS to be twice that, and that sets my TS and the period of D. So if you want a wider bandwidth, then I use a higher FS.
I see.
Okay. So in that sense, G of tau is indirectly linked to this thing. So if it were a true analog FIR filter followed by a simple sampler, then you would not have this issue. What is happening is that although conceptually it is like an effective filter G of tau followed by a sampler, the way I'm doing it, it's kind of merged together. I cannot separate out this G of tau and this sampling. The sampling is inherent. So that is the indirect requirement. So I can make my G of tau wider, but then I have to increase my TS accordingly. Otherwise, the filter operation is going to get disturbed. So it is fundamentally a time varying circuit, a periodically time varying circuit. But as far as the samples are concerned, it is acting like a linear time invariant system. That's what I'm showing you in the bottom left, right? So that is where the relation is coming from.
Okay.
Okay, that's where the constraint is coming from.
Okay.
We looked at it for a little while, not a lot, to see if we can shape the filter within the band. But we could not yet find any interesting way, and I have a small group, so we kind of moved on to other aspects of this thing. But that could be possible.
Okay. I see. So if you want to let's say I have a very large oversampling ratio, then the only option I would assume is to increase the number of time interleaving slices, basically.
If you want to do a very large oversampling ratio, yes.
Okay. Okay.
Yeah.
I see.
So this has been designed such that Nyquist sampling and nothing else. But like I was saying, if you typically do oversampling, then you want to be able to control the shape inside the band.
Right.
Inside the Nyquist band. So I think it may be possible, but we have not found a solution yet.
Okay. Thank you.
Okay, any other questions out for Professor Pamarti? Well, Professor Pamarti, thank you once again for a very, very enjoyable and excellent talk.